Welcome to solverfy.
Hi there. So for this problem, we have a positron atom that consists of a positron and an electron. In the board-like model, the two particles rotate in circle about their common center of mass. So for this, the first part of this problem, we need to calculate the reduced mass of a positronium atom in terms of the mass of an electron. So we need to find the mass of the positron. So we are going to say that is the total mass. Now, the equation or the formula for the reduced mass is given like the following. Because the system is composed of an electron and a proton, we are going to call the mass of the proton MP and the mass of the electron ME. So the formula for the reduced mass is mp times me, the mass of the proton, times the mass of the electron, over the sum of these masses, the mass of the proton plus the mass of the electron. Now, we know that the proton and the electron, the positron is is an antiparticle of the electron, so the only thing that changes is its charge in comparison to the electron. So their masses are the same. So the mass of the positron is the same as the mass of the electron. So with this, we can simplify this further. So we can say that we are going to obtain in the numerator that the mass of the electron squared, and in the denominator we will have 2 times the mass of the electron. So we can simplify this further by eliminating one in the numerator or one in the denominator. So we will have that this is equal. The reduced mass is the mass of the electron half of the mass of an electron. So that's the reduced mass of this system known as positronium. Now, for part B of this problem, we are told to determine the orbital radius of its ground state electron. So for this, we use the following equation to obtain the radius R1, because we want that when the ground state, so the ground state it's n equal to 1. We know the equation for Rn for any given value of the state. So we will have that this is n squared times the Planck constant squared over p times the total or the reduced mass times the charge of the electron. So as you can see, this reduced for R1 as the following. When we introduce 1 in here, we will obtain 1 in there. So we will have this. Sorry, this is not bar H, it's just H. So this corresponds, and this at the same time is equal to 2 times the atomic radius. So we know the value for the atomic radius. That is this A sub 0 is also known as the Bohr's radio and has a value of 5.29. Sub 0 is 5.29 times 10 to the minus 11 meters. So when we plot that in the equation for R1, we obtain that this is 2 times that value. So we obtain that the radius for the ground state n equals to 1, it's approximately 0.106 nanometers. So that's a solution for part B of this problem. Now for part C of this problem, we are asked to find its ground state energy. So for that, we also use a known equation. So again, we are using that the mass corresponds to the reduced mass, and n is equal to 1 because that's the ground state. So we know the equation for the energy of any n state. So that is minus m, the charge of the electron square, epsilon sub 0, or the vacuum permittivity, a times n squared h squared. So with this, we can see that when we are obtaining for n equal to 1, this reduces to the following: minus mt squared over the vacuum permittivity squared, a times h. And this corresponds to the ground um, the ground um, the ground energy of the 1/2 of the ground energy for the hydrogen. So we will have that this is minus 13.6. That's a known value, electron volts. So when we multiply this by 1/2, we obtain that this is minus 6.8 electron volts. So that's the solution for part C of this problem. So for part B, we are told to, well, we are told that the longest visible light emission wavelength for ordinary hydrogen is of a given value. I'm going to put that value in here, D. Oh, I'm going to put this in black. So that wavelength is a value of 656.3 nanometers. And so with this information, it says in Earth, and it is for the n equals to 3 to n equals to 2. So we're passing from that states n equals to 3 to n equals to 2. So with this, we need to calculate the wavelength for the same transition in positronium. So we want the wavelength. So the energy, I'm going to put that in here, the energy. So the energy is the energy difference between the levels. We need to find the energy and then solve for the wavelength. So the energy, the equation for the energy, we know that is the Planck's constant times the speed of light over the wavelength. And we know the value for the for that, and we also know that this is equal to minus 6.8 electron volts. That's the same, that another equation for the energy. This is the energy that we obtained for this case for the positronium, and we will have that this is equal to 1 over the initial state, which is 3 squared, minus the final square, which is 2 squared. So when we calculate this, we obtain that the energy for this case is going to be 0.9444 electron volts. So from this, we need to obtain the wavelength. So we just solve for that. We obtain that the wavelength is very straightforward from this equation. That is going to be the Planck's constant times the speed of light over the energy. So we introduce all of these values and we obtain that the wavelength is 1310 nanometers. So that's the wavelength for this case. So this is it for this problem.